The slide set is about precast, pre-tensioned bridge concrete girders. We're basically going to be looking at Caltrans, the California Department of Transportation, standard typical I-girders or I-beams that they have in their manual. Here's a cross section of a standard bridge supported on I-girders. Total bridge width is given at 35 feet. You have 6 girders. The spacing from a girder to a girder is exactly 6 feet. And with that you have 5 spaces, and the girder spacing is going to be 6 feet to a total of 30 feet. Depth of the girder is going to be 3 feet and 6 inches as a typical. So it's going to be 42 inch deep. Once you include here the slab thickness, which is a concrete topping, is going to be 7 inches thick, total of 4 feet and 2 inches. You're talking here about 50 inches for the total depth, including the concrete deck of the bridge. The slide here, it shows the pre-casting bed, which is also the pre-stressing bed. You have here a reinforced concrete slab on grade. It works as the bed, which is the formwork. You're gonna have here the concrete section of the I-girder. It has some formwork, which means the sides of the I-girder. You're gonna put here some abutment. One is gonna be in the middle, then you're gonna have 2 end abutments. Cable is gonna be straight, it's gonna be running across. Maybe 2-3 beams if you like. You're going to be applying here the tension from one side. So you're getting the anchorage through the end abutment from the right hand side, as you see in the top picture. On the other side, you're going to have the stressing or the pre-stressing jack. Now you apply the pre-tension to the cable, and after that you're going to be anchored from the left side. After that, within the formwork, you're going to be putting the concrete. Now the concrete is going to get hardened at a certain point, at a certain age of the concrete. Once it reaches the F prime CI that you're going to be using in your analysis, and let's say maybe about 3 to 5 days, maybe 7 days, you can start here by releasing the pre-stressing cables from each side of the abutments. After that, you can trim or you can cut the cables at the face of the girder itself. Once you release the stressing jacking and the anchorage, and once you trim, once you cut the cables, the strands, what's going to happen here, you'll transfer all the pre-stressing force to the girder itself. Since we have simply supported girders, and since the pre-stressing is going to be at the bottom, is going to be straight, I'm expecting that I'm going to have here a camber. Total shortening that's going to happen here to each one of these girders is going to be equal to delta sub ES. This is going to be the elastic shortening. Elastic shortening means the change in the length of each one of these girders. The final length here is going to be equal to L, which means the original length of the girder subtracting delta sub ES. Caltrans 2012 manual includes a list and certain recommendations for the precast girder types and the recommended spans. According to this table, you have here the girder type in the first column, and then you have the possible span length, which means, for example, if you'd like to use California I-girder, California I-girder can work start from 50 feet all the way to 125 feet. It is recommended to use it between 50 to 95 feet only. The second one, which is California Bold T-girder, it works between 80 to 150 feet. It would be great if you can use it between 95 and 250. Which means if I have here 100-foot span, it is okay to use California eye girder. It's gonna be more economic, and it's gonna be also preferred to use a California bulb T-girder. Now let me see, why would I say that? If you go here to the California eye girder, it is true that it's gonna be possible to use it according to this table, because the possible range goes from 50 to 125. Now our bridge here has 100-foot span, but it is preferred if you can use it between 50 to 95 feet. It's gonna be more economic, it's gonna be simpler and more preferred if you can go here to the California bulb T-girder, because in this type of girders it is preferred to use it between 95 to 150. Since ours is gonna be 100, it's gonna be more suitable to use California bulb T-girder. The third type of girders that also is recommended to be used is called California wide flange girder. The flange is relatively wider than that of the eye girder and the bulb T-girder. As you see here, you can use it between 80 to 200 feet. Recommended to use it maybe all the way to 180 feet. Usually, once you have here a simple span bridge, the depth to span ratio is going to be somewhere between 5% to 5.5%. Once you go here to continuous or multi-span structure, this is going to be ranging, which means the depth of the span is going to be ranging between 4.5% to 5%. This is a standard that you're going to see here when you do a design for Caltrans eye girders. We have here a few pictures. The first one on the top left hand side, it shows a bulb T. The bulb T, as you see here, is going to have a good flange size on the top, but at the bottom here you're going to have a good size here to encase mini cables if you like to. If you look here at the right bottom picture, this gives you the wide flange girder. You see here that on the top it really have a good wide flange. The bottom is going to be also a flange. It is not like the bulb T. In this slide here, it shows the wide flange girder, a closer picture of it. As you see here in the top, you see lots of rebars that sticks up. This is actually going to be the ties that you're going to be doing inside the girder itself. You're going to be leaving them sticking up, and then later on, after you install them in place, you're going to be bending these dowels horizontally so that they're going to be embedded into the concrete deck of the bridge. Here is the schedule for the California standard eye girder. In the California standard eye girder, I'm going to start here by looking at the picture, try to understand it. It shows here the width of the top flange to be 19 inches. The width itself is going to be standard of 7 inches. And on each side you're going to have a 6 inch. Which means for any size of this standard eye girder, the width thickness is going to be 7 inches and the top flange is going to be 19 inches. This is kind of standard. You're not going to change this. It doesn't matter what depth you're going to be using or what girder mark that you're going to be using. Now total depth is going to be D. H is going to be the distance or the clear height of the web. At the bottom you're going to have the same thing. You're going to have here the bottom flange or the bottom section of the girder is going to be a width of 19 inch with 6 inch and then another 6 inch here for the flare. I'm going to have here some variables, and this variable is going to be based on the mark that you're going to pick and choose, which means the type of the girder. You have Y top, you have Y bottom, which is the same as C top and C bottom. You have the eccentricity measured from the CG of the section, the centroid of the section, to the centroid of the pre-stressed strands. It shows here in the picture, it says CG of the pre-stress force. Now look at the girder series, which means the type or the mark. It says here California I-36. This means it's going to be standard I girder with a depth of 36 inch. Look here at the depth, it says here 3 feet and 0 inch. Let me go down, it says California I-42, it's going to be actually 42 inch deep. And then you have California 48, it's going to be the 4 feet deep. And then 54, 60, 66. And it shows all the information related to this girder, which means based on this schedule here, you can pick and choose the girder series, which is the type or the mark of the girder, and then you have all the information related that you may be using in your analysis. You have H, you have the gross section area. The gross section area, you have the moment of inertia. About the CG, you have Y bottom, Y top, S bottom, S top. You have an R, which is rate of acceleration, and you have also the weight of it as in pound per foot. In this current slide, you see here the California bulk T girder, and look at the width of the top flange. It's almost 4 feet, it's 47 and a quarter. The whip thickness is going to be standard of 7 and 7/8 of an inch, almost 8 inches. Same thing, I'm going to have the schedule here. It includes all the types of this California BT, the bulk T. It says here 49. California bulk T BT 49. It means the depth is going to be 49 inches. Yeah, 4 feet and 1 inch is going to be 49. And then the list goes on. You have the depth, H, gross area, you have moment of inertia about the CG, and you have Y bottom, Y top, SB, ST, R, and also the weight. Now there's something here unique about this type of bulk T girders. This bulk T girders is going to include pretension strands. As you see here, you have the small circles like the half-inch ones that you see here at the bottom. Also, you're going to have, as it says here, optional post-tension ducts, which means this system here, you can have some pretension cables, and then after you move it to the site, after you install it, you can also have some post-tensioning that you can do to this girder. And with that, you're going to have pretension and post-tension. Usually, the pretension strands is going to be used so that you're going to be able to support or to pick up the girder, transport it to the site, install it in place, and with that the beam should be able to support its own weight and the concrete topping, which means the concrete deck of the bridge. The post tension is going to be used to resist the life load. Both of the post tension and the pre-tension should be able to support all the total weight that you have in there, including ultimate load and including service load when you do the checks. The slide here, it shows the bathtub girder. This bathtub girder is actually used to build a box girder. Now what is missing here is going to be the concrete deck on the top, or the concrete slab if you like to call it this way. If you look here at the schedule, it shows here California top TU B 55, the depth is about 55 inches, and then after that you have the 61, and certainly you have all the section properties that you need to do your analysis. This also includes pre-tension and post-tension, if you like to use a post-tension. Most likely, the pre-tension strands is going to be used so that you're going to be able to transport this bathtub girder from the casting yard to the bridge location. You're going to be able to hold it, you're going to be able to lift it up, put it in place, and also it's going to make it able to support also the concrete deck of the bridge. But most likely this strands is not going to be able to make it a bridge, is going to be able to support the life load. in order for you to support the life load, most likely you're going to be using the post-tension cables. Both of the post-tension ducts or cables and the pre-tension strands, they're going to be able to support the total load, including self-weight, additional dead load, this additional dead load, which is the concrete bridge deck, and the life load of the bridge. The California wide flange girder is shown in this slide. It has a width of 4 feet for the top flange, and the width here at the bottom is going to be 3 feet and 9 inches. It's going to be all here pre-tension strands. You have certain standard dimensions that you cannot change, and of course you're going to have some variables. The variables are going to be the depth D, eccentricity E, because it's going to be controlled by the location of the CG, Y top and Y bottom, and R. Also, this schedule here includes all the variables that you can have with all types of this wide flange girder. This slide, it shows the California wide flange post tension. There's a slight difference between this type of girders and the previous girder. The previous girder, you don't really have a chance to put post tension. It doesn't come with it. It's going to be only pre-tension. And look here at the call out for it, like the type. It says California WF48, and here we have additional term here, which is PT, the post tension. And this post tension, you're going to have here some optional ducts, and with this optional ducts, you should be able to put some post tension strands. And with that, you can have pre-tension and post tension girders. It's going to be a combination of the two concepts, if you like. We have also the voided slab. Voided slab is good when it comes to short spans. So in short spans, you can use this voided slab. Voided slab is going to be all pre-tension strands. It's going to come with it, and most likely it's going to be straight because you don't really have a chance here to drape it. Don't forget here that the depth, as you see here, the depth is 18 inch, or the depth is going to be maybe 20 inches, or in some cases going to be 12 inches. So in a case like this, you don't really have a chance to drape it, and most likely it's going to be straight. You have other shapes for girders, like we have the delta girder, we have the box girder, it's complete box girder if you like. We have also the double T. Double T is going to be very similar to that we use in parking structures. Now let's look here at the cases of loading. We have here stages in cases of loading. At the beginning, according to the picture here that you're looking at, you'd like to look at stage 1. And the stage 1, this will include the transfer time of the pre-stress force. On the left hand side, it shows the girder, and it shows the location of the pre-stress strength. Just under the self-weight of the girder, you're going to have here this stress distribution. On the top is going to be compression, at the bottom is going to be tension. Now the stress itself is going to be equal to M sub G, which means the gravity, weight of the girder, or M of the girder, divided by S, which is the section modulus. Of course, you're going to have here S top and S bottom, and with that you're going to have the top and bottom stresses. So top and bottom stresses doesn't really need to be the same, unless the section has a CG, which is right at the mid height. Now look at the effect of the pre-stress. Only the effect of the pre-stress without considering the eccentricity is going to be equal to the P, which is initial pre-stress, P sub I divided by A. Here you just call P, which is fine, because in some cases you may transfer the force at F sub Ci. Other cases you may leave it till you gain the full strength. So this left it as just P divided by A. After that, you're going to have the effect of the eccentricity of the strength. As it shows here, it's going to be P multiplied by E, which is eccentricity. Eccentricity here is going to be the location of the strands measured from the CG of the section. So you should note here that this is going to be P times E. It is not really PE, the effective pre-stress. No, it's going to be P multiplied by E. And this is going to be creating a moment in the section from the pre-stress force itself. You divide this by S. For the top stress, it's going to be S top. For the bottom stress, it's going to be S B. You add all of the stress shapes to each other, which means that you combine all of these values. In the top, you're going to have here some tension force or tension stresses. At the bottom is going to be some compression stresses. So it is expected that just under the self weight of this girder that you may end up with some tension on the top. And certainly you have here limits when it comes to the stress on the top, stress at the bottom. Stress on the top here, it needs to be within, and of course you have here the limit. It shows here T, which is the tensile stress, is going to be less than or equal to roughly 9.5% square root of F prime CI, or is going to be 200 psi. This provided that you don't have any bonded reinforcement. The bonded reinforcement is going to be the non-tension reinforcement, like the conventional reinforcing. An example of it is going to be, let's say that you have two number 5 or two number 6s. So if you don't have it, this is going to be the tensile level stress. If you have some bonded reinforcement, in this case your level tension is going to be equal to 0.24 square root of F prime C. When it comes to the compression stress, maximum allowed compression stress is going to be equal to 0.6 F prime C. Now the second stage, we call it here stage 2A. Now we have the stress that we just determined, and the stress here is going to get locked in. Locked in means that now the stress is going to be within this girder. Now you move the girder to any place with this stress that we just calculated out in stage 1 is going to be in there. You cannot really change it. Now after this, you put the girder in place. Now you start to put the concrete topping or the concrete deck of the bridge. Once you start to put it, now the concrete is fresh, and this girder here is supporting this fresh concrete. This is why you see here the first stress distribution is going to be for the stage 1 analysis that we're just done with. Now we need to add the effect of the slab weight. The slab weight means the concrete deck weight. What's going to be supporting it in this case is going to be this girder, the bridge girder. It's going to be causing here compression at the top and tension at the bottom. Essentially the load is going to be coming from the top to the bottom. The stress here is going to be equal to the moment coming from the slab weight, the additional dead load if you like, or superimposed dead load. You divide it here by S top and S bottom for the top stress and the bottom stress. Now you need to add the two stress diagrams to each other. With that, most likely you're going to have compression here in the top and compression at the bottom. Compression at the bottom here cannot be more than 0.6 F prime C. So you got to be careful about this. And this here called stage 2A is going to be during the erection. And in this case here, concrete topping is not hardened yet. Now let's look here at case or stage 2B. You're going to have more additional dead load if you like. Now the concrete slab is hardened, which means it's going to be able here to resist some of the stresses. Now let's take here the stress distribution that we determined from stage 2A. Stress calculated here from this stage 2A is going to be most likely compression top and bottom. We're going to be taking it as is. Now we're going to be adding more moment to it. And this moment is going to be coming from the additional dead load. This additional dead load is going to be all like, for example, the wearing surface, which means the pavement that you can do above the concrete deck. Is going to happen because the barriers that you installed there is going to be from any other stuff that you'd like to install to the bridge. It may also include any piping. If you have here any piping is going to be installed within the bridge deck itself or right below the bridge deck, also you need to include it in there. Now the entire section of the girder and the concrete deck is going to be used here to resist the new stresses. This is why you need to figure out this additional moment due to the additional dead load and start here to divide it by S. Now S is going to be for the entire section. Now you start here to take the stage 2A, you add it now to the new stresses coming from the additional dead load, and this additional dead load is going to be including again pavement, is going to be including the barriers or the rails, it's going to be including any piping that you'd like to install below the bridge. Now you start to take it and add it, and with that you're going to end up with stage 2B concrete stresses. You're going to notice here in the top that there's something there about the stresses in the compression, and this is very similar to what we have seen in your midterm. Now in stage 3, once you open the bridge to traffic, which means now it's going to be the service life of the bridge. Now what we need to do is to take the previous stresses from stage 2B and put it as is. And you see this here in the next stress distribution to the girder itself. So look here, all the way in the left hand side, it shows here the bridge itself is going to be the composite, which means it's going to be the girder and the concrete slab on the top, the concrete deck of the bridge. And then it shows here stage 2B, which means the stresses that you just calculated out in the previous slide. You have the life load. You're going to be taking here the life load, start to use it. Now take here the moment due to life load, and you divide here by the section modulus. Now this section modulus is going to be included the entire composite section, which means it's going to be based on the girder and the concrete slab on the top. Now add the two distributions to each other, to the stresses, and with that you're going to have here the final stress distribution throughout the depth of the bridge. And you see here that the tensile stress cannot be more than 0.19 of square root of prime C, and this is actually giving the service level stress distribution. Now we need to talk about whether we're going to be keeping the strands straight or do we need to harp it. Harp it means to drape it, which means change the location of the strands within the beam depth itself. You understand that usually we'd like to keep it at the CG at both ends of the girder, but this is going to be costing money. Now to drape it is going to also have certain advantages, and we have also a few disadvantages. The first advantage here is going to be more efficient when it comes to the flexure design, because you're going to have very clear eccentricity, and also you're going to have less camber. Also, having this draping is going to help with the shear strength, because think about the fact that this sheared section of the girder is going to be under compression, which means the interlocking between the aggregates is going to increase, and this is going to increase the shear strength. Also, once you look here at the end of the girder, which means the end blocked zone, you're going to have here less stresses because you don't really have eccentricity on the end block. If you keep here the pre-stress force right at the CG, it means the stress right at the face of the girder is going to be equal to P over A. There is no eccentricity, nothing there, and you don't really need to have to provide any reinforcing. Talking about non-tension reinforcing, which means a bonded reinforcing at the end to protect spooling of the concrete on the top of the beam. What's the bad thing about this? About the draping thing? It's going to be number one, it's going to be the safety, because guess what? How would you bring the cables down? Now it's going to be pretensioned. which means that you need to pull these cables down in the middle of the beam somehow. You need to have certain expense because you need to have your mechanism to keep it at the bottom. Now you start to apply here the tension force. So it's going to be number one is going to be the safety, because you need to have here more parts, and of course number two is going to be higher cost. Let's look here at the diagram above and the diagram below in the picture. As you see here, you need to have a mechanism to keep the cables in place, to keep them at the bottom. Once you apply here the tension at both ends of the abutment, what you're doing here, you're applying a force. It's going to be pushing the whole system up. And certainly you need to keep it down. So you need to have here some foundation, and you're going to have here a jack at the bottom. The jack at the bottom is going to be used to bring this cable down. So you're going to have here some mechanical losses, and of course you're going to have additional cost. Good thing about it, you're going to be here reducing the amount of stress. It's going to be, of course, certainly it's going to be easier to design. You have here more flexibility when it comes to design. Now at the end of the girder, what do? We can debond here the cables. Debond means that we can do here separation between the cable or the strands and the concrete. How do you do this debonding? By providing conduits with which, or certain wrapping with which the strand is going to be wrapped with, or is going to be going through at both ends of the girder. Good thing about it, it's going to reduce the stresses in this location. And it's going to be much simpler when it comes to fabrication. Also with that, you don't really need to have any hold down devices. The hold down device is going to be this device in the middle that you're going to be using to pull down the strands. Now what's going to happen here, you're going to have more compressive stresses, which means your design here for the compressive strength, it needs to be higher. Also, you need to make it work. So you need to figure out which cables can be debonded and at what location, and what's going to happen here with the reinforcing and the camber. So it's going to be much more complicated when it comes to design and analysis. Here is the strand debonding. You could maybe run it through conduits, cables, or you can just run it by wrapping it with some sheeting. This sheeting is going to be doing here debonding between the strand itself and between the surrounding concrete after you pour it. Now we have three precast bridge types. The first one is called precast pretensioned girders, and in that you don't have any post tensioning. Everything here is going to be done in the casting yard, which means in the factory. The second type is going to be precast post tension spliced girder. In this system here, you can bring two girders, connect them for continuity, and in most cases you're going to have some pre-tensioning, and certainly you're going to have post-tensioning that goes with it. And the pre-tension is going to be only there just to be sure that you should be able here to move the bridge component, the girder, from the yard to the site. You should be able to carry it, transport it, put it in place. The last one is called here precast segmental girders. Lots of box girders, like the bathtub system, is using this system here, which means it's going to be pieces, you put them all together. It's going to be some pre-tensioning, if you like, for these segments or pieces, and after that, of course, you're going to have here the post-tension is going to come and combine it all together. In the schedule here, it shows each one of these bridge types, the possible span, and the preferred span, if you like to get economical design. For single span bridges, Most likely we'd like here to use a seat type abutment. The seat type abutment, it means at the end of each bridge girder you're gonna have a support to it, and the support is gonna be a seat type, which means that you're gonna have here a full support of the girder at the end. This picture here is taken from a bridge, and here's the bridge number, and that was done in California. When you have multi-span bridges, you'd like to provide here some continuity in the girders. And you can do this in a few ways. You can have your drop caps. I'm going to show you here some pictures in a minute. You're going to have this inverter T caps, or you can have integral caps with precast post-tension girders. Here's the drop cap. Look what happened. Drop cap means a cap supports the girders. It's going to be 100% below the girder itself. Like look here at the central pier. You're going to see here that you have the pier, then you have a cap. The white cap here is able to provide the seat for both sides of the bridge. Look what's going to happen. Here's the section through it. You have the piles, which is come from the bottom, and then you have the cap, it's going to be full of reinforcing, and then you're going to have two pads, bearing pads, and then you have the two girders coming, each one's coming from each side, and they just sit on the top of this cap. We call this drop cap because it's going to be lower than the two girders. If you like here to see more drawings to it or more details, if you like to see here some continuity, now you come here in the top, and then you provide the concrete slab or the concrete deck is given the top. You can have also a central wall that goes between the two girders, but at the end you need to have here a cap is going to be able to support or provide the seat for both girders from each side. You can have this inverted T cap, and this is very similar to what we use in apartment structures. It's going to be like a girder that runs across. It has two ledges, so the ledge here is going to come, and then the girder itself is going to come pre-notched already, and it's going to be sitting on the ledge. All the way in the top, you're going to be putting here the concrete slab, which is the bridge deck.